Okay, guys, Fires Frost here, and we're going to talk about my programming project, which is to break down the double pendulum second order ODE into several coupled first order ODEs, and then solve it so we could plot or use its data, use the equation for whatever the heck we want. So this is a double pendulum, which is two masses attached to lengths that are attached to a central point where it is anchored. Of course, that these are frictionless, and they are massless, rigid bodies, and uh, we're basically trying to break down the second order derivative. So the actual equations for the pendulum of motion can be found by using kinetic potential energy and the position of the bobs, uh, turning them into a Lagrangian. I don't even know how to pronounce it, and then coming up with the Euler-Lagrange differential equations for theta 1 and theta 2. So this is what they look like. That's what they are simplified for 1 and 2. So it's these. We're trying to solve those. And we're going to, I'll show the program when I'm done. But basically, we have these, and we want to break this up into a form that is usable for an equation, because this is a big mouthful to put into the program. So when you're doing these second order kind of things, you want to break them down into first order because MATLAB, a program like MATLAB and derivative solving programs really just don't work too well with second order or other symbolic equations. So we're just going to do some basic math here, and these will be substituted for these, but that's just rewriting the entire thing. But what's the important part is we have also these. Yoink. And 3, 4, 6. So we have A, we have B, we have C, we have D, we have E, and then we have F. So when we rewrite it without all of the mumbo jumbo, you can turn such a complex looking problem into a really easy one. So that's U2 dot plus B V2 dot equals E, and C V2 dot plus D U2 dot is equal to F. So we basically just turn this really big clusterfuck of a second order uh, ODEs, coupled ODEs, into these problems, which look so much simpler, as well as our original two substitutions. So we have U2 dot is equal to uh, theta 1 dot, and V2 is equal to theta 2 dot. There. These don't really matter since we're trying to solve for these. But now that you notice, we still can't really do these because these are functions of u2 and v2. So we're gonna do a little substitution. So yoink. We have a u dot 2 plus b v2 dot equal to e. We're gonna solve for u2. U dot 2 is equal to E minus BV dot 2 over A. Now we're going to plug it back into this problem. See V dot 2 plus D E minus BV dot 2 over A is equal to F. And then we're just going to do some math. CV dot 2 is equal to DEA minus BV dot 2 dA is equal to f. And then we want to isolate our thing. So we have plus c v2 dot minus d b v2 dots over a is equal to f minus de over a. We'll multiply by a. We'll get a c v dot 2 minus db v dot 2 equal to f minus de. And then we do v2 dots of ac minus db is equal to minus de divided by ac minus db. I think I messed up something here. I'm way too tired. It doesn't matter. My whole point is you basically do these systems of equations, you solve it. I know I wasted all your time. How much time have I spent on doing that? It's been 6 minutes. I don't care. Let's just get right into the program. Here. This is what we solve it for. You should get ED. Well, how close was I? Multiply A over A. So AF over DA is A multiply. Okay, I think that would have done it. Oops. That's not my point. My point is you create these systems of equations and you basically just have your pendulum. So here we are in our project pendulum, and this is our main. In the function, we have our function y prime is equal to project pend, which is any function handle as a function of time and your y. We have our initial parameters with our lengths, our masses, and our gravity. These can be changed, but they don't really make a difference. I mean, they do, but they aren't the radical difference. So after that, we build a y prime uh, matrix of 4 zeros because we're going to fill them up. And then when we have A, B, C, D, E, F, like I mentioned before, in here, these are our A, B, C, D, E, F. It's really just random constants that aren't really going to change that we just plug and chug right back in. We don't have thetas. We instead will just use y's because it's easier that way. And then we have the system of equations. So we have four equations. Y prime is equal to y2, y3 is equal to y4, y prime 2 is equal to this, which is what I was trying to solve for, and y prime 4 is equal to that. And then here we have a y prime is equal to y prime apostrophe. Apostrophe inverts your operators because as it is right now, uh, we have a vector, a vertical vector, but then actually let's do a is equal to zeros for 1, and then we do a that, and then it goes there. It just flips it vertical, horizontal. Neat little thing, and it's the end. That's the only function. What's important here is the actual project here. So we have some basic clears, more parameters. We reiterate the pattern, the parameters because they are mentioned. They are used in both. Strangely enough, we have our initial condition. Uh, I mean, these are initial conditions, but these are the big initial conditions. So we have T-span, which is our time in seconds, which you can change, but it doesn't really matter. We have theta 1, which is the first angle. This is in radians. Uh, it's worth noting that the smaller the initial value, the less chaotic that the pendulum undergoes, and that makes a lot of sense, because if you think of a double pendulum, uh, how do you can I just paint bucket? Does paint bucket do anything? Nope. Uh, okay, if you think of a pendulum, uh, theta here is 0, and theta here is, I don't know, small. Gravity will act upon it and it'll go this way, but the force is a small force, and it will just kind of go like this, right? However, if our initial is really fucking big, uh, we will have big, because the potential energy is super high up here, and it gets turned into kinetic energy, and you have that, and then since it's on a joint, it's gonna like spin like that, and it's gonna go back, and it's gonna spin like that, it's gonna spin like this, and it's gonna spin like that, it's gonna spin like. I hope you get what I'm getting at. Oh, this looks kind of like a face. That's so weird. Uh, I don't know. This is a weird nose, but there we go. Going back to the problem, we have our initial thetas, the theta primes, these are the derivatives. These are normally going to be 0 99% of the time. Then we have we create a little matrix here that is just the thetas. And then we have our actual ODE, which solves our here. As you can see here in our input, we have ty. These are some of the parameters. The input, the OD45 is the name of the derivative solver. At project pend means it recalls project pend function. We have our initial condition, which is, I mean, this is our time sequence, time span, 0 to t span. Uh, and why not, which is our initial condition here. Here we have position of masses. These are important to keep track of because they keep in mind thetas here. These are just filling in indexes because it's not as robust manually putting these in. Then we have some basic charting things. This is what is this? Oh, here we go. This is mass 1, 2 position over time. This is theta 1 over 2 over time. And this is a movie that I forgot to label. So we're going to run it. It's going to take a while because it's thinking. Da 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 da. It's worth noting that ODE 45 has a variable step length. So here we go. Here's it in action. Here we go. I don't know why it's being slow right now. As you can see, the initial theta was really small. As a result, the pendulum itself is going to be very small. As you can see here, this is the... Oh, what the fuck? Wait, it changed. Yeah, this thing kind of bugs out if you let it run too long. Let me run it again. Here you go. You can see as a position 2, mass 2 follows a pretty predictable path. Uh, these are bugs. I actually have like, these are like, I don't know why this happens. Let me try to run it again. We'll just regenerate it. Uh, here, as you can see, theta 1, theta 2, it oscillates pretty regularly before it disappeared because it just doesn't play nice with the movie. But we're gonna amp up theta. Let's say theta 1 is, I don't know, 6.2. Theta 2 will be, I don't know, 1.4. And then we'll run it again. That's not as crazy as I thought. Oops. just make this 4.2. Once you go over 2 pi, it's just not as crazy. Here we go. This is wacky. Look at this fucking thing. It just goes batshit crazy. Remember, this is actually pretty accurate to what it looks like. It Look at it. It just goes bonkers. We can mess with the lengths. Length 1 will be 2. Length 2 will be 1.5, 2.5, 2.5, 1, 1.5. Run it. This looks fucking crazy. Here we go. Look at this. Here we can see it really just makes some more circles when this is longer. Uh, there you go. Yeah, so this is what I worked on. This is what our project was. Uh, it was surprisingly extremely hard, mainly because I had no idea what the double pendulum formula is. I also didn't know a lot of the things, especially programming. A lot of this I like first time learning. I wanted to share it with you because I literally have spent so much fucking time uh, on this project. So I hope I get a pretty good grade on it, and I'll catch you later.